up here to remind you this, whenever you use L on Y, what it is. Let's kind of summarize what we did class last time. We looked at the linear differential equation L on Y equals 0, which was the homogeneous case, and then L on Y equals G of X, the non-homogeneous. What we found is that to solve the homogeneous equation, you always do that first. If a differential equation is of order n, then you're required to come up with n linearly independent solutions. We refer to those as the fundamental solution set. And then we showed that the most general solution to the equation, to the homogeneous equation, L on Y equals 0, was just a superposition of these n linearly independent solutions. By superposition, I mean just a linear combination. And that's how we get the arbitrary constants, and we'll get n of them if it's an nth order equation. If we had initial data, then we could evaluate those things numerically, those coefficients. When it came to the non-homogeneous equation, what we found is that the solution to that, the general solution to the non-homogeneous, consists of two parts. First, you find a particular solution, right? That's basically L operating on YP. That's gone, okay? L operating on YP equals G of X, okay? And we found it could be any particular solution. And again, the particular solution is not unique. But then to get the general solution of the inhomogeneous equation, we just take the particular solution, you recall, and add to it the homogeneous solution. Summation of Ci yi of x, I equals 1 to n. That's the general solution to the inhomogeneous equation. Okay? So whether you're solving the homogeneous and inhomogeneous, the first thing you're going to do is look at the homogeneous equation, right? To get the n independent solutions, little y1, little y2 up to yn. And then, if it's not homogeneous, all you have to do is find any particular solution and attach that. And that'll give you the general solution to the equation. Okay. Well, now, the rest of a couple of weeks, we're going to actually develop techniques to get the homogeneous solution, to get the particular solution. Okay? One of the techniques that's very popular is called reduction of order. Okay? And it works even for an nth order equation with variable coefficients. So let me consider the equation. This is called reduction of order, so you'll see where it is in the book. So we're going to look at the equation L on Y is equal to 0. L on Y is that thing in red. So it's a homogeneous equation. A reason it's called reduction of order, okay, the book really doesn't do a real good job of this, and I'll show you why. What it does is a certain substitution that's used, and it basically reduces the equation from, say, order n to order n minus 1. Okay? And the idea of reduction of order is that you have to have one of the independent solutions to start with. And many times, if you're doing a physical problem, either from the physics or just looking at the equation, you can by inspection see one of the homogeneous solutions. Like I said, you can just look at it and say, oh, y equals x squared is obviously a homogeneous solution. But then the second one is a little more evasive. You know, you just can't get it so easily. And reduction of order is perfect for that because it allows you to reduce the order of the equation. You know, it's analogous to having like a polynomial, okay? Suppose you got to find the roots of a third-degree polynomial, okay? There is actually an algorithm, but usually you say you only know quadratics. And then you look at the polynomial and you say, oh, r equals 1 is a root. Then r minus 1 is a factor from your high school algebra, right? Then you take the cubic, you divide by r minus 1, you get a quadratic, which you can solve. Analogously, this is going to happen over here with differential equations. Okay? So let y1 of x be a solution to the homogeneous equation. So L operating on y1 is equal to 0. Okay? So you just happen to know one of them, and we'll do this with an example right away. Let me show you why it reduces the order of the equation. So the procedure is someone gives you, or by inspection, or by the physics of the problem, you can ascertain one of the homogeneous solutions. And suppose that it's like, you know, second order, then we need another independent solution. But this will work even for nth order. And here's the trick. What you do is you go back and you say, let y of x, which is going to be the solution to this equation, let's write that as the product of y1 of x, which is known, times an unknown function u of x. Okay? So I'm looking for a solution to the differential equation now, and I'm taking advantage that I know one of the homogeneous solutions of y1 of x. And then I multiply that by some function u of x. Looks at this point, it makes it more complicated, but you'll see how it simplifies it. let's plug in this expression and get the differential equation on u and see what happens. And I'm going to show you that if the equation on y is nth order, the equation on u can be written as an n minus first order equation. Okay. So let's just crank out derivatives. This the book does not do, but it's kind of a good background for it. What's y primed of x? Okay. You see you're going to get y1 primed of x times u plus y1 du dx just by the product rule, right? So therefore, the first derivative of y involves the first derivative of u and u itself. Okay. Let's go to the second derivative, y double primed of x. Using the product rule again, I'm getting y1 double primed of x times u. Here I pick up a y1 prime u prime, and over there I pick up also y1 prime u prime. So I get 2y1 prime du dx, and here I get a y1 times the second derivative of u with respect to x. And all I want you to observe from this is that the first derivative of y involves u and du dx. The second derivative of y involves u, du dx, and secondary with respect to x. So obviously the third derivative of y is going to involve u, du dx, second derivative and third derivative, etc. So what happens now, okay, we're not going to do this, all the algebra, you just kind of do it in your head. When we see the nth derivative of y with respect to x, we'll plug in terms of u. We'll do that over here, and over here. And what we're going to land up with, if you rearrange terms, is an nth order equation on u with new coefficients, not necessarily those, right? Because here you have a0 of x times what? y1u. What do you have over here? You have a1 times, then you got to plug this stuff in. So every term is going to pick up a u primed, etc. But we can rearrange it because it's linear in exactly that form. And what's going to happen is that the equation will now transform to the following. It'll now look like some function bn of x times the nth derivative of u with respect to x. Same exact form as that, except the coefficients are different. Plus b sub n minus 1 of x, n minus first derivative of u with respect to x. Right? Plus b1 of x du dx plus b0 of x times u will equal 0. So this looks kind of silly. All we've done is done a lot of algebra and got an equation that's about as difficult as the one we started with. What advantage is there? Here's the advantage. We know that y1 of x is a solution to the homogeneous equation, right? So therefore, from what we studied last time, if y1 of x is a solution to the homogeneous equation, any constant times y1 is a solution, which means u of x equals constant is a solution to this equation. U of x equals c, where c is arbitrary constant, must be a solution to above equation, the one I just wrote above. Okay? Again, the reason for that is that we started off and we said y1 of x is a solution to the homogeneous equation, so therefore, if I set u of x equal to a constant, it's certainly a solution of the original equation, and this is equivalent to the original equation, so therefore u of x equals c must be a solution to this equation. Go into this equation and plug in ux equals c, where c of x is, where c is an arbitrary constant. All the terms go to 0. And what are you left with? b0 of x times c is equal to 0 for arbitrary c. The only way that can happen is if b0 of x is equal to 0. Okay? Therefore, b0 of x actually goes away. It will actually see that. We'll do a problem and we'll see it. Okay? What's the advantage now? Now your differential equation has the nth derivative with respect to x, n minus first derivative, and then it stops at the u dx. So if I let the u dx equal v, what happens? I get v prime, all the way up to v n minus first derivative. So I reduce the order by 1. And for a second order equation, this would be very useful because then n is equal to 2. And what would happen then is that we'd have something times a second respect to x, another function of x to u dx, and then it would stop over there. If I let the u dx equal new v, let's say, I get a first order linear equation on v, and I know how to solve first order linear, right? We know how to do that. Let me illustrate this, okay, on a problem. Okay. And again, the theory will tell us that, that U is going to drop out. And if it doesn't, then it's something that we did wrong. Here's an example illustrating reduction of order. Okay, so to recapitulate, all you need is you have a linear differential equation, okay, homogeneous, and you start off with someone gives you, or by inspection, you can see one of the homogeneous solutions. This will allow you to determine the second homogeneous solution. And if it's a second order, then you're finished, right, as far as homogeneous equation goes. Let's look at the equation y double primed minus y is equal to 0, okay? I claim that a solution of that is e dx. You can just plug it in and see, right? If y is e dx, y double prime is e dx, yes, e dx is a solution. Okay, so that's the solution of the homogeneous equation. The procedure I will now do is mimics the general one. I'm going to let y of x now in this equation be the product of the known homogeneous solution, which is e dx times u. Okay? And now I'm just going to plug in that expression e dx times u, and I know from the theory that I should not have u will disappear from the equation. It'll only have a u double primed and a u primed in it. So let's just calculate our derivatives now. Okay, what's y primed of x? By the product rule, it's e dx u plus u primed, right? Using product rule, you get derivative e dx u plus e dx u prime. Okay, what's the second derivative of y with respect to x? Use the product rule, differentiate e dx is e dx u plus u prime plus e dx. Now let's differentiate inside. I get u prime plus u double prime. Or the second y with respect to x, I can pull out an e dx on everything, and I get an e dx u double prime from this guy, right? E dx u prime, e dx u prime, so it's 2 e dx u prime. And then I get, looks like an e dx u. Okay, that's my second y with respect to x. Okay, let's see what the left-hand side of this equation comes out to be. L operating on y, which in our case is y double prime minus y, is just going to be e to the x. I'm getting u double prime plus 2u prime plus u, right? That's my y double prime minus y, which is just e dx u. And as the general theory predicted, the coefficient of u goes to 0. See e dx u minus e dx u. Just exactly as we had predicted. Okay. So now, what's my differential equation? I want this to equal to 0, right? Everything now is multiplying by e dx, so let me divide by e dx, and my equation on u now is the second derivative of u with respect to x plus 2 du dx is equal to 0. Now, the idea is that, yes, it's a second order equation on u, but it's a first order in u prime. So let's go over here. So I'm basically going over here now. Okay. I'm going to say let v equal to u dx. So you'll see that's the first order equation. Second with respect to x now is going to come out to be dv dx plus 2v is equal to 0. Can't be simple, right? First order equation. Matter of fact, it's separable. Right? So I get the differential of v divided by v plus 2 dx is equal to 0. Let's integrate that. We're going to get the log of v over here, right? Plus 2x. And what happens is that I can put an arbitrary constant, but I'm going to, basically put it to 0 because I don't need the most general solution. All I need is any function u, okay? You'll see that actually if you put in the arbitrary constants in there, you'll get not only the new solution, but you'll recover y1 of x also. So log v plus 2x is equal to 0. That says that the log of v is minus 2x. So v is what? E to the minus 2x. Okay. Now we just need one more step. We have to get u. U is the integral of v, right? So it's the integral of e to the minus 2x dx, which is minus a half e to the minus 2x. Okay. Now we can get our second solution. Our second solution, I'll call it y sub 2 of x, to differentiate it or distinguish it from the first solution. It says we look for our second solution of the form e dx times u. What happens when I take that u and I multiply by e dx? I get minus a half e dx times e to the minus 2x is e to the minus x. Okay? And again, what you could really do is set y2 of x equal to e to the minus x, because any constant times a solution is a solution, right? Or, I shouldn't say this or, but you have to remember the words here, right? It's e to the minus x. This is not equal to this, but the idea is that we're looking for a second independent solution of the homogeneous equation. You could just as well call it e to the minus x as well as minus half e to the minus x, right? Constant doesn't affect it as a homogeneous solution. So what happens now is that this second order differential equation has two linearly independent solutions, e dx and e to the minus x. And the general solution, of course, would then be y equals c1 e dx plus c sub 2 e to the minus x. That's the general solution. Yeah.
What happened to the second derivative before you switched over to
over here?
v? Yeah.
Oh, what I did is basically I noticed that u is absent, so I let the u dx equal v. So the second derivative of u becomes dv dx. Okay? That's basically the whole reduction of order business. Okay. Now, in some textbooks, they just leave it like this, and every time you have a second order equation, you got to go through this whole rigmarole. It comes out, and actually your textbook does this, and I'm going to do this, is that we actually can solve the general second order equation, okay, and get closed form solutions for the y sub 2 of x. And it's much more convenient, I guess. The question is then, it's a messy formula, and the question is, what do you do on an exam? Do I allow you to have a cheat sheet, or do I put it on? We'll worry about that later. But for the homework, it's certainly beneficial, okay? In other words, we're going, like I said, you can just remember